Okay, well, welcome. It's 3 o'clock. We're going to get this party started. Welcome to our session on power quality. As I been telling everybody, I know we still have people coming in on YouTube. I'm not sure how many people we've got out there. Let me just take a look. I know we have quite a lot of people signed up for this. So I think what I'm going to do, Dan, is during our introductions, I'm going to leave the Menti code playing so that those who are coming in, we use that Menti code 245528 as your registration for professional development hours. If you're looking for that certificate, it's a PDH certificate, and it doesn't have. It's not like it's recognized. Not like I went to different states. I know some states get really particular with what they recognize and don't recognize. My certificate basically says you were here at the beginning with this Menti code. I take that registration. At the end, I'll display a second registration code for your exit. I compare those two. Whoever was here at the beginning, documented. Whoever was here when we ended, documented. I will issue a professional developed two PDH certificate to you. So that's sort of how I run this program. We're loading up on YouTube. We got 121 out there now. I'm not sure, and so they're loading in, guys. All right, so why don't we do this? So again, welcome. My name is Thomas Dimitrovich, and I've got with me three very smart individuals that so I'm the looks and they're the brains on this one. And so I guess we're gonna go right down the line this way. So Eric Hurd, why don't you start us off? Why don't you just give us a little description of who you are? Just give us your background.
Yeah, so I'm Eric Hurd. So thanks everyone for joining. So I am the Power Systems Experience Center engineer. So I work for Dan, who is obviously sitting to my left, I guess would be. And so I started here a couple years ago, a little over 2 years ago. So I've been with Eaton for about 11 years. So I came from the services group. So I was working in what's called the Power Breaker Reconditioning Center, which is part of the switchgear modernization. So I'm kind of like the nuts and bolts guy to this. So a lot of hands-on stuff as far as ripping stuff apart and getting down and dirty with all kinds of the equipment, electrical equipment, breakers, and medium voltage, low voltage type stuff. So still learning at this stage that I'm at. So there's a few great people on this call that I'm going to be the one asking questions. I'm still trying to learn stuff too. So I feel like I'm catching on to some of the stuff, but still have a lot to learn. So looking forward to doing this and doing whatever comes forward from this.
Awesome. Well, we are very happy to have you here. And then next in the lineup, drum roll please, Dan Carnevale. Take it away.
Hey, Tom. Hey, thanks a lot, Tom. No, I'm excited to be here too. I'm the manager of this facility, the Power Systems Experience Center here in Pittsburgh. And basically, power quality is my passion. So I've been doing a lot of this for years with ABB and Westinghouse previous to Eaton, troubleshooting power quality problems forever. And this is absolutely my favorite thing to talk about. So really excited to be here. Eric's a little bit humble, but he definitely knows a lot more than he leads on here. So we'll definitely like to hear from him. And Santino's a great asset to the group too. He'll give you a little bit of his background, but we're super excited to be here today. Thanks.
Awesome. Thank you. And then finally, Santino Graziani.
Hey, hello everyone. My name is Santino Graziani. I am an intern here. I'm kind of like a full-time, part-time intern. I've been here for over 3 years, and that's because I'm actually a graduate student as well at the University of Pittsburgh, working on a PhD right now. I've been working under Dan for about that time, 3 years. So I kind of look at myself as like his apprentice, and I've learned a whole heck of a lot. So I'll kind of bring the perspective of fresh out of, say, undergrad or even a master's degree. And, I've learned a lot here, so I know, enough to be a little bit deadly, but I do know that what you learn in undergraduate school and what you actually deal with in the field is very different. So I will be also monitoring the chat. So hello to everyone, Manuel, David, Gustavo. I'm going to try and do that. We want to make this as interactive as possible and kind of make it an environment where there's no such thing as a stupid question, because a lot of these things can be quite confusing, especially if no one ever taught them to you directly. Because, in undergraduate school, we learn the concepts, but we don't get a working understanding for a lot of these things like power factor and harmonics and the like. So I also just want to say that I'm humbled because just 3 months ago, I was helping Tom with audio-visual issues with his streams, and now I actually have the honor of being a guest. So thank you, and welcome to the stream.
Nice.
You just gave away my secret. See, they thought I was fixing all these issues. Jeez.
No, I don't think they knew that.
Oh man,
That was my job at the start of the pandemic, was just watching your streams and helping out. So I learned a lot.
I appreciate all the help too. So the other thing I want to recognize, so as looking through the registration, we have quite a few countries represented as far as registration goes. So, I mean, we've got obviously we got Canada, the U.S., we got Costa Rica, Guatemala, Honduras, India, Indonesia. And then I never heard of OMAM, OMAM, and that's out there in the Middle East. So just, I guess, south east of Saudi and so Saudi Arabia. So we got Spain represented, Trinidad, United Kingdom, United States. So Costa Rica, Colombia. I want to make sure I don't miss any country, because I think this is really cool that we're taking social distancing network from a global perspective, and really reaching out across the globe. And what I love about it is we're getting to talk about a very important topic of power quality, which is important to everybody. So, and that's what we're going to include our journey into today. So again, for those of you just joining us, I'm going to be pretty soon, that Menti code is going away. That's 245528. Go to menti.com and sign in if you want that professional development hours. So please don't forget that. I don't want to get those emails where you say, I came in late and I didn't get the code. So please sign in. I know we've got quite a few people out there already on in YouTube land. So be mindful of that. All right. Having said that, Dan, Eric and Tino, I guess we should begin. I guess we talked earlier when we were trying to plan this out that we were going to hit a few key topics, right? We're going to talk about what is power quality and a few other things like that. I did put together some reference documents. I don't know, Dan, if you think now's a good time to just walk through some references, or should I bring those up as we get into our discussion?
Yeah, it's probably a good idea to bring them up, and then we'll refer back to them later.
All right. So I put together some documents, some reference documents that if you're into the whole power quality thing, if that's your journey in life at this point, whether it be a problem you're trying to solve, or part of your educational process, or just a process, part of your career, just trying to understand this technical topic, a few standards come to mind. IEEE Standard 1159, and I did grab the latest version of it. There's a 2019 version. And the previous version was done in 2009. So this is the recommended practice for monitoring electric power quality. Monitoring, what's our motto, Dan? If you don't monitor it, you can't manage it, right?
That's right.
So IEEE Standard 1547, 2008. This is the application guide standard for interconnecting distributed resources with electric power systems, and that whole concept of connecting into a utility, and power quality is important to the utility, just as important as power quality is to you from the utility. So power quality is important for all of those players involved. I can't forget about the color book series, which we know the color books are sort of going away. There you go. Dan's got his. I got mine, but it's behind my sheet behind me in my library. People think that I'm up on Mount Washington in Pittsburgh, but I'm really sitting in front of my bookcase. But in any case, Standard 1100, powering and grounding electronic equipment. I used this book heavily when I was doing the security system at Crystal River Unit 3 when I worked down at Florida Power Corporation, because we were doing a lot of signaling and whatnot, and that was really critical and important for security. Go ahead.
Hey, Tom, let me say something about that. One of the most important things I think out of that book is really the definitions part, because one of the things that's kind of crazy with power quality is, you get a lot of these terms, glitch, brownout, just dirty power, all those kind of things. And the definitions part in that book is super important, so everybody's on the same page. I think that's probably one of the most important things. And one of the good things that IEEE did with that also was say, here's the words that you probably shouldn't use because there's confusion associated with these words. And so I would just recommend at least looking into that section of the book for everybody.
Awesome. And that's probably right up front, right?
It is. Yeah, right in the first chapter, I think it is.
It's chapter 2, definitely. Well, in my book.
Yeah, chapter 2. Yeah. And then if you look at like 2.3, words to be avoided, that's kind of my favorite section because that's where you see things like glitch and dirty power and, spike and stuff like that. So.
Oh, yeah.
Again,
look at that.
It can be confusing if everybody uses different terms for the same thing, right?
Yeah. Absolutely right. In terminology, I mean, it's so important in a lot of different areas, but especially, think about all the different countries and different people we have represented. We have to all be using the same terminology because it could be perceived differently based upon just your perspective on your what your background is from a language perspective as well. All right. Another one, IEEE Standard 1250. This is a 2011 version. I believe is the latest. I went up on IEEE and found the latest copies. IEEE Guide for Identifying and Improving Voltage Quality in Power Systems. So, Dan, this one gets into actually improving voltage quality, not just identifying it. A lot of stuff I see deals with just at least trying to understand what power quality is and how to recognize it, but it's really important to understand how to fix the problem, right?
Yeah, and I think the difference there is, again, like trying to improve it versus like the C84 standard, I think it is, where you basically define the levels that utilities have to prescribe to. So like plus or minus 5%, plus or minus 10%. And those things are important as well, but from a power quality standpoint, this one, is a good one.
Excellent. And this was I got this one. This was what I did was I went up to IEEE's site and I did a search on power quality just to see what kind of documents are out there. This one popped up, which was the guide on interactions between power system disturbances and surge protective devices. I never, to be honest, I don't know, Dan, if you have familiarity with C62.48, but I've never really looked at this document all that much.
Yeah, I haven't spent much time with this one, but you and I had talked a little bit about the UL standards for surge and even really capacitors and other things. And I think the statement there would be, how does that differ from some of these ones? Because the UL ones are mostly around the safety aspects of those devices, and people will say, what does the UL stand for, whatever. But basically, it doesn't mean that it's going to be better for power quality necessarily, or in terms of capacitors, better for, harmonic correction or anything like that. So I think that's the distinction where these ones are trying to be more specific. I don't have a lot of experience with that particular one, though.
Yep. All right. Yeah, me neither. This one was IEEE Standard 519. Now, I missed this one. I can't believe I missed it. And I sent that over to Dan because you forgot 519, Tom. Recommended practice and requirements for harmonic control in electric power systems. And it looks like the latest version of that is the 2014 version because I had to go up and grab it. That's why I missed it. It wasn't on my computer.
Well, that one was interesting because for years they've been trying to update that one since 1992. So really that one was a really long time in between. And the interesting thing with that one in particular, Tom, I think is probably more than any other standard I've seen is, most standards go from like this thick to like, bigger. But this one actually went from thick to pretty concise. And so what that means is they're very prescriptive about just harmonics in there and how, what kind of things to consider at the point of common coupling and things that are important there. So that's probably the most interesting part of that particular standard, but I do like how they summarize that one.
So let me ask you a question, Dan. In most of the stuff I get involved with, when it comes to documents like this, there's always those controversial topics that, I don't know, either it's a manufacturer or some group has heartburn over, and then they argue and fight. Do they have the same type of issues when it comes to documents in these types of reference documents with regard to power quality, or is pretty much everybody on the same level?
Yeah, the reason is because if you notice the first couple words, right, recommended practice. So that's where it's not a you must or you shall or whatever. It's kind of like this is what you should do.
Right.
And then the enforcement of that is also a little different, right? So where we run into it, for example, let's say a water treatment plant buys a whole bunch of variable frequency drives, and our salesperson comes to us and says, hey, this is, correct us because the designer said we have to be below this IEEE 519. And, so all of a sudden it starts to become confusing. And the designer's asking a question, the utility's asking the question, the end user's asking a question, and all of them have sort of their spin on what's important and what the bottom line is. And it's interesting. Sometimes I'll tell them, hey, you don't need to do anything. Don't spend any money. And they all kind of look at me like, well, and I said, well, what's actually your problem? And let's go back and identify that first, and then decide if it's, again, this is a recommended practice to make your system better. If your system's okay, why would you spend money, right?
Yeah.
That's the ambiguity of it.
Yeah, that's a good point. Very good point, and very good distinction between a recommended practice and a requirement or a code. IEEE guide. This is C62.48. I think I already showed that. Did I show that earlier? What was the other one? Yeah, 62.48. Same document. There you go. UL 1449. Surge protective devices. You wanted to throw this one in there. So now here's what I always tell people. A lot of people won't get the UL standards. I mean, as manufacturers, we get the UL standards. What the industry references is what, I mean, I called the UL White Book. They no longer produce the UL White Book. It's now Product IQ, I think, is what it is. I believe that's what it is, and I could try to call that up as we get into discussions here. But I think it's called Product IQ. And what's great about Product IQ is that's a document that Product IQ. It's an online resource that basically takes out of the UL standards what, in general, people need to know about to be able to apply products, if that makes sense. It's a free resource that UL provides to the industry. They take out of the UL standards what's important for the proper installation and application of the product, and they make that available to authority-having jurisdictions or design engineers or just about anybody. So I think that's an important thing, and I'll try to call that up later, and maybe we can look at what Product IQ says. And what you'll find in Product IQ are things like what's required on the labeling of the product, the voltage ratings, and things like that, how it's supposed to be applied. But UL 1449 has seen some changes, hasn't it, Dan?
Yeah, I think I'm going to ask Eric to do me a favor and grab Mobile One there if you can, and show maybe those two melted surge protectors over there. And I want to address that from the standpoint of, what happens. Why has UL 1449 changed so much recently? It's really all about, again, previously when MOVs would fail and cause fires and things like that, there had to be some changes that came in that basically would say, okay, we need to, put in some onboard fusing or onboard circuit protection to take those MOVs out of the circuit, because most times, surge protectors don't generally fail from surges or transients that we're going to talk about. They usually almost always fail from an overvoltage. In this case, it was open neutral. In the other case, it was the generator regulator went haywire, and the generator was putting out 320 volts. So, if that happens, and the surge protector, we always say, people say they're self-sacrificing or whatever, but at the end of the day, if it fails and burns your house down, that's a problem. So the latest changes in the 1449 were really mostly around those kind of things and how you test and make sure that they're going to work well.
Excellent. Yeah, that's a very important aspect to make sure that you get that you have the right products doing the right thing for you, and the standards continue to develop and progress. So, some good feedback, good background.
Hey, Tom, we got a couple questions in the chat.
Oh yeah, beautiful. What's up?
One was, can we list the IEEE and UL references somewhere?
I will do that. You know what I'll do is I'll put that in the link below this video after it's done. I will make sure that I include the reference documents. I did already put some links to references that are in the description to this on my YouTube channel. So I'll put that down below and make sure that that's there.
I'll take a note as well.
Perfect.
Another question, I think maybe for Dan. So thanks to Dan in the comments for that question. And then this is from Ahmed. Dan, about using the dynamic voltage restorer. What's your opinion on that? A dynamic voltage restorer? I'm not sure what that is.
Yeah, so DVR or sag corrector, they're similar kind of things. We can actually, show sort of a demonstration of those. There's actually a video on our website, and Tom will share those the website links and stuff with you as well. But they actually work well comparatively. The reason, and we'll talk about that when we talk about voltage sags, but basically they're like a batteryless. Think of it like a batteryless UPS, mostly for voltage sags. Some of them have some short-term storage. It depends, but for the most part, they're more industrialized as opposed to a standard UPS that you're gonna have to worry about, air conditioning and things for batteries and trying to maintain that. So when we talk about the sag part, we'll come back to that. But I appreciate the question. If we have more specifics, I can always have a sidebar as well.
Thanks, Dan.
Excellent. All right, so I guess those are all the references, and I'll put that list as Santino noted. We'll put that list out there down below on the YouTube channel. So the next segment of this is basically a discussion around what is power quality, right? I think there's a lot. I know in my mind when I hear power quality, I have a few buttons that go off. I think of maybe voltage sags and swells. I think of harmonics. But it goes a lot deeper than that, doesn't it, guys? Like what kind of other kind of things that would do other parameters? How would you describe power quality or poor power quality, Eric?
So I'd say first things, like you said, so voltage variations, just like you mentioned. So the sags, the swells. There's also going to be the transients. So like the surges, where we just talked about surge protection and stuff. So that, and then as well as the harmonics, which we started touching on. So again, that's going to be another thing. And then also grounding can't be forgotten about. That's going to be another key thing. But and then something as far as the voltage variations, because I know Dan likes to talk about several different types of voltage variations and how that's such a big thing. So I always ask him, like, why not? Like I just asked him yesterday. I'm like, how come they never really bring up current variations? Like, why are we always, when we're metering and we're analyzing stuff, why is it always voltage?
Hey, Dan, can you mute yourself while he's talking? He's coming through your mic.
Yeah, I got it. Sorry.
Thank you. It's okay.
The other thing I forgot.
What's that? I'm afraid to ask. I don't know.
I totally forgot about the quiz.
The quiz. I was going to say. I thought maybe we were saving it for like a special thing.
Here's the thing. I rely on you guys, and I rely on others to remind me.
So excited.
We're so used to watching all your other ones, though. You show them at different times. Whenever you remember it.
Man. So what do I got to do to try to you guys? I need a straight guy. So
hey, Tom, let's go through the quiz.
So here's what we got. So we're going to review the quiz, and I sent this out to everybody who had a registration. I believe it went to most everybody. If you did not get the quiz and you want to take the quiz as we go through this, if you now this isn't a part of registration. If you go to menti.com and enter 381055, it's a series of true or false questions. And this is going to help guide us through the discussion today, but we're going to look at those. And here's the deal, guys. If they get them all right, we're not going to spend time on the discussion. What do you guys think? Make sense? All right. So what I'm going to do is I'm going to start walking through these examples. And if anybody wants to, who didn't take this short quiz, it's anonymous, completely anonymous. I don't know who's taking it, so no answer is a bad answer. Just go to menti.com and put in 381055. All right, so here we go. Let's take a look.
And just to say again, Tom, like Santino said before, like we want this to be as interactive as possible. So
yeah,
feel free to put questions in the YouTube chat. I'm monitoring that. I don't know if there's a Facebook chat, Tom, but I don't have access to that.
Yeah, I'm looking on that now. I don't see anything. I'll look at I got the Facebook chat up. I'll make sure that there's if there's anything coming up there. And you watch the YouTube.
Congratulations to Bruce B. He got an 8 out of 10 on the quiz. Thanks for letting us know.
Oh, hold on, Bruce. We didn't even tell you what the right answers are. Here's the thing. Here's the funny part about that. He only gave himself an 8 out of 10. I would have said I got a 10 out of 10. Jeez. All right. So power quality in my facility or in my home is driven by what is provided by the utility. True or false or not sure. 122 respondents.
Well, my first thought would be, isn't the utility guaranteed to give you a certain quality of service?
Okay, that's probably true. Is that true? I mean, does the utility guarantee power quality?
That's a good point. So Tino, that's where the point that Eric brought up just a little bit ago before we started talking about the quiz comes into play. So they're required to give you a certain voltage range, right?
Mm-hmm.
And if they do that, the rest is kind of up to you. And then there's certain requirements that allow them to do short-term things. Like, for example, in a lot of their metrics, they don't need to keep track of things that are less than 2 minutes. But what happens to something that's less than 2 cycles with your electronics now? So going back to, we'll talk about the definition later, but yeah, things that happen from what's going on inside your facility. If you're a chemical plant and you're starting big motors, that's kind of up to you. And you might even hurt your neighbor.
So Dan, could there be a less than 2 minute power quality issue that happens on a daily basis, such as the starting of a nearby motor that could affect your quality, but they wouldn't pick up on it?
Oh, the 2 minute thing is more around full interruptions because they call things momentaries and things like that versus full interruptions. But again, that's on the voltage side. But things where you and another neighbor are conflicted with, problems that they might cause you, that's where harmonics come into play. That's where, large motor starting, other types of voltage flicker would be requirements there. So that's another standard, Tom, that would be another interesting one to talk about. But
so they don't guarantee you any like total harmonic distortion minimum or anything like that. They assume it's so stiff that really it's just what's on the other side of your transformer that you're doing that's causing the problem, or your neighbor.
It comes into play, right? So it depends on where you're at in the system, and we'll talk about that with the harmonic part of it. But you can actually screw yourself up pretty badly, and then that's really not up to them. Yeah.
And what you said too is pretty cool.
I apologize for that.
Yeah, what you said too, Dan, about the interruptions, like if it's under 2, so you could be sitting at your house without power for everything could be shut off for a minute, or whatever it might be. They don't even consider that an interruption, do they? The utilities?
Well, again, it goes by these definitions. So there's momentaries and temporary kind of things, and there's what they would call an outage if they have to roll a truck.
Yeah.
We talk about that a lot. What do they do to get the power back on quickly? They use reclosers. Well, it's not so much that they're doing a worse job today, but what are we putting on our system? We're putting all kinds of electronics. So as soon as we have a recloser now, every alarm clock in your house resets, and so we get annoyed by that. Whereas before, things would just come right back on. So that's the bigger difference.
So if the utility is giving you great power quality and everything's looking good, can you still have power quality issues in your facility?
For sure. Yeah, you can put, again, if you go back to what Eric said, we have voltage issues that are, sags and interrupts and stuff that might be coming from outside. But it also could be coming from large motors in your facility, but also harmonics are generally caused by the customer, and 80% of the transients that we see are caused by stuff within your own facility.
Yep. Yeah. All right. So the right answer to this one would be false, right?
Eric, you're rubbing your mic.
I am?
Yeah. Is that you?
I don't even have it. I don't think my mic's all the way up here. I don't know.
I think that sound was coming through.
All right. Thanks.
Hey, let's see. Manuel, do I sound too loud still, or is this good?
All right. So I have a surge on my power conductors coming into my home. I won't have power quality issues. True or false? Boy, there's only 5 people that said true. So I think, the answer to this one's obviously false, right, guys?
Yep.
Piece of cake.
Yeah.
Do we need to?
And the reason is just because there's all those other types of problems, not just surge, right?
Yep. Yeah, surge is only one aspect of power quality. Well, this one didn't get too much controversy. All power quality issues are solved by proper grounding and bonding. So, is the answer false, guys?
False.
False.
Yes, false.
Same reason. Same reason.
Same
Yeah.
reason.
It's one of four. Yeah.
Now, here we go.
that's a little better here.
Controversy. Always mount your surge protective device in a location that can be seen. Remote mounting is preferred. Well, what say the panel of experts?
False.
I got a false vote from Santino.
You're getting a false.
I got a false vote from Eric.
Yeah, it's definitely
I'd
false.
rather not. I'd rather not see it and have it working.
Yeah.
But
Yeah,
if you can't
what-
see it,
what
how
I'm
do you know
saying
it's
is-
working?
A lot of times what happens is people mount them in a place that's kind of convenient and comfortable for them to physically mount it. But every inch of lead length, that gives you 15 to 25 volts of let through. So if the thing was supposed to clamp at 300 volts, it might clamp at 2,000 volts, and there's no point in having it there. So the further away you put it, the worse it's going to operate. And, you know, I had people tell me even in one of the facilities I was doing an audit in one of our own facilities at one point. They said, well, we put it over there on that wall like 25 feet away so we could see, when we walk by the door, we could see the lights on, make sure it was working. So, yeah, definitely you don't want to do that. Long lead lengths are a problem.
We have an interesting comment on the YouTubes. Safety devices should be accessible. So that is somewhat of a good point, but if you mount it so far away, it's no longer a safety device. It's just a blinking light, would be my response to that.
Yeah, I guess it's important. You know, we talked about the lead length, so let's just talk a little bit more about that. So the basic guidance that I think every surge protective device manufacturer tells their customers is to mount that surge device as close to the bus, right, as close to the equipment as possible, because I think, Dan, I don't want to overlook that detail that you said. Every inch adds how much voltage to let through?
It's about 15 to 25 volts. So like if a surge protector was supposed to clamp at 400 volts and it clamped at, or you put it 3 feet away, it could clamp at, say, 1,000 or 1,500 volts. There's Eric showing you an example right there. You might get one with 3 feet of lead length. Ideally, and again, they're tested. Here's the important thing. They're tested with 6 inches of lead length. So when it claims to clamp at a certain level, if you can't get it connected at that level, every inch is going to add about 15 to 25 volts.
Okay, so why would a surge protective device manufacturer ship a product with more than 6 inches of lead length?
I knew that was
Sometimes it's physically impossible to do. Right? Go ahead.
Yeah.
But if you think about it, I mean, that's something I think is really important. And sometimes I think the wrong message is received when you have that lead length that comes out of the box and it's very long. And that's why it's really important that people understand you really want to get that as close as you can beyond that 6 inch. Even if you're less than 6 inches, do you get better clamping voltage, Dan? Or is it just basically what the performance is based upon the standard?
Yeah, it actually is. And let me think in the PowerPoint deck, I can tell you which slide to pull up. We can go back to that later if you want. It basically can be, if it's supposed to clamp at 400 and you put it directly on the bus, so it basically has 0 inches of lead length, it clamp at 350. It's going to do better than what it would be otherwise.
Okay. Now, do you know what slide that is? Because I have the PowerPoint up.
Okay. Yeah, if you go to slide, it looks like 33.
Okay, 33. There we go. Oh, yeah, I remember this slide. Yep.
Okay, now, Eric, do you want to just talk or show them where that is on that? Maybe if you put the mobile camera on there for Eric.
Yep.
I'll talk through as you kind of pointing to the different locations over there.
All right.
So the one on the left is integrated. Okay, the ones on the, yeah, so it basically looks like the one he has in his hand. Okay, it's bus mounted. Okay, now show the two on the right, Eric. So in that panel board on the right, there's one that's like 12 inches away, and there's one that's about 3 feet away. Okay, and again, that 12-inch one is about as close as you could electrically couple it on the outside, and that's why I told him you have to add a little bit. and the one is 3 feet away. So now, if you go back to the PowerPoint slide, you can basically see on the top one, can't see that exactly, but that's right around, I have to make that a little bigger on my screen here. The top one, it's clamping a little bit around 400 volts. The second one with 12 inches, about 500 volts. The third one with 36 inches is over about 1,000 volts. And then we did one with no protection that goes up to about 5,000 volts. And what we did was we put just to give you an idea here, we put a 7,000 volt transient out to show you how that would actually clamp or not clamp. So even in the first one, we've had it clamp less than, like I said, 400. You can see that first little blip on there was just, a little bit of an overvoltage there, but sometimes right around 350 or so, we'll get that one, depending on the actual event. And again, that waveform is a 1 megahertz type, lightning strike type waveform, a 1.2 by 50, and then it's an 8 by 20 once it goes through a spark gap. So those are very, very fast waveforms, sampled at 6 megahertz.
The first one is integrated. The second one is right next, that's 6 inches away?
12 inches away.
12 inches away. This third one, which goes up to 976 volts let through, is
30. That's about 36 inches away.
3 feet away. And then this one is without surge whatsoever.
Yeah. So let's just do a quick math thing, right? So if you say that it's supposed to clamp around 400 or so, and it's 36 inches away, it's 30 inches too far. 30 times 20, is an extra 600 volts on top of the 400. That's how you get to 1,000. So it's a pretty simple, you know what I mean?
Yep.
Yeah.
So your equipment downstream sees more voltage the longer you put that lead.
Yeah, the interesting thing is the surge protector, the MOVs inside, are actually clamping at the level that they're intended to clamp at. The problem is, Eric showed you those wires. Those wires are carrying the current. This is 1 megahertz current, and the inductance of the cable, 2 pi times the frequency times the inductance, that current flowing out on that wire, it becomes a very, very, very high impedance, right? So the current going out and coming back actually has to go across that high inductance, and that's why you get that voltage drop. So at the MOVs, it's 400 or less, and out at the panel, like you said, and everything downstream sees that higher voltage.
Yep.
So just Dan, or just both of you, I guess, to everyone, as far as adding on to that, like getting those kind of waveforms and stuff there, like you said, it's a really, really fast event. Is any meter going to pick, like as long as you have a meter like monitoring, is it going to pick that up, or do you need a special kind of meter for that?
Good question.
Like a really high sampling meter or something? Like a Power Expert 8000?
Yeah. No, that's a good point. So one of the things we do with that demo is actually show that's 20 samples per microsecond with that meter. And what would happen is you can picture that waveform going through and coming by. You would actually miss, data points on the, let's draw it on the fixed camera over there, Eric.
Yeah, I'll mute it.
Hold on.
Let me know when you're on the camera. Okay. So if I have this waveform like that, can you hear me okay?
Yep.
Okay. And let's say you take a data point here and here. Well, you would totally miss that whole waveform, right? But why would you do that? Well, you're thinking this event is only 1.2 microseconds from here to here. 1.2 microseconds, okay? Now, what we were saying is we're taking 20 data points per microsecond, so we would get a pretty good resolution of that. If you zoomed out on this, what you would see is a sine wave, and on the very peak of that sine wave or somewhere along the sine wave, you see something that just looks like this, and it almost looks like it comes back on itself. That blown up is what this is. So if you took a data point here and here, you completely missed that. So the sampling rate of the metering and the instrumentation is super important. And that's why, we'll talk about it later, but kind of looking at what the symptoms are. When something blows up, it's going to be a surge, more than likely, or something like that. And so looking at the symptom is kind of really important to figure out what actually happened, even if you don't have the metering to know that.
Right. Right. Very good point. So that brings up a good discussion point of making sure that you have the right meter. I know when we do metering from energy management, the big deal is you have to have the metering class CT because you want that accuracy as opposed to a relay class CT, because relay class CTs, that sweet spot is the very high fault currents. So on a meter, when you're doing power quality monitoring, you have the meter, the sampling rate, which is driven by the microprocessor that's in that meter, right? Is there, I mean, this is there a special CT or other equipment that you need to get good pictures of your waveforms?
Yeah, so we're doing those voltage measurements directly, but if you were to go through a PT for voltage, a PT is going to basically cut it off about 5 kilohertz, and a CT, most CTs are 3 to 5 kilohertz as well. So the problem there is you might not, it might be a filter for the things that are going on, and you might not even see it. So there are high frequency CTs, like Pearson makes some, for example, that we've used with oscilloscopes that have the high sampling rate that you can actually measure and resolve that. But again, sometimes knowing what the problem was allows you to know what's going on, without actually measuring it. But most of the time, in other words, going by the symptoms. But if you're able to measure the voltage, especially on a 480 volt system like we have here, it's really important to get that resolution if you think it's a problem related to transients. If you think it sags, no problem. You don't need that resolution. And why would you spend the money on that, right?
Right, right. Good point. All right. Anything else on that one? Is that you feel comfortable we beat that horse? We good? All right. So the right answer to this one is false, right? You want to make sure it's closer. Like somebody said, Santino, I think put a point. You want to, if you can, as long as you can see those lights that it's on and off, that it's actually functioning, you'd want it as close as you can. And for those who are looking for the check, hopefully you learned something. So next question. Current harmonics have more of an impact than voltage harmonics. Another controversy. Look at this. We got 5644 and we got 28 that are not sure, 15 that says there's no such thing as current harmonics. Man, Dan, you're pulling the wool over my eyes, buddy.
Eric, hold it back.
I know.
So here's the thing.
Down here.
Yeah,
I like nervous. That. So here's the thing.
Here's the thing. This one's a good question, Tom. I'm glad you kind of did this one because really, current harmonics have more of an impact, maybe, but their voltage harmonics also have an impact. So both true and false would be true, if that makes sense. Either true or false could be accurate because we didn't say the current harmonics cause voltage harmonics because they actually usually do. But current harmonics cause heating, voltage harmonics cause misoperation. So, if you have current harmonics, you might not see enough of an issue from heating, but you might see an issue from misoperation, multiple zero crossings or, something misoperating.
Right.
But it doesn't mean it happens more frequently one way or the other. And so that's the reason I think either true or false could be accurate.
Okay, so but for those 15 people that say there is no such thing as current harmonics, I mean, hopefully they can walk away knowing that there is such thing as current harmonics. I mean, so Dan, I mean, do we have any in our slide deck? Is there any pictures? What is a current harmonic? I guess you would look at the amp, you would look at your current waveform, and you would have to see higher frequencies in that current waveform to be able to tell. Because like on surge, the waveforms that you were just showing were voltage waveforms. But you could look at your current. Do they call that? You have a percent THD for current as well as voltage.
THD, yeah. So let me find the slide for you, Tom. Okay, so I think on yours it should be slide 120.
120. See this now. All of those in YouTube land and on Facebook land should be thanking me for not putting you through over 120 slides.
I wanted to go through each slide independently.
There it is.
And then as a backup, we'll go to 130 after this. But so go That one's a little bit different than the one I have on mine. Let me see if I can find which one you're on. I might have put a couple different ones in, but let's see. Go up and down from that one. From this is resonance. Go up a little further. Can you go to the top of the harmonics section? Oh, there's the beer analogy. Just in the, it'll be a little way up from there. The first part where it says harmonics.
Harmonics, third harmonic.
Probably around where the infrared scan is there.
Right
I got
here?
a link of a picture of the harmonic current. I don't know if you can open links. I'm trying to Google stuff in real time as we do this.
Yeah, no, I have it on. Like, there's one that is just called harmonics, and there's a percent THD slide and stuff like that. Tom, I don't know if that's on there, but
Harmonic basics.
anyway, let's see.
Harmonics and
Apologize for-
generators, notching currents. Yeah.
Just make them full screen. I'll be able to tell which one you're on there. But anyway, the answer is, yeah. So there's one right there. So on that, in that particular case, you can see voltage and current harmonics. Okay, and in fact, when you're running on the utility source or the generator, you're getting the same current. In other words, the double hump thing in the middle is roughly the same, but the voltage distortion is better on the utility and worse on the generator, because the generator has, think about a normal transformer. So Tom, if you were doing a system study, what would be the impedance of a transformer? You'd what? 5.75 or something, right?
Yep.
So, yeah. So then if you have a generator, it's going to be 18% or 20%. So having harmonic currents flow through that impedance, you're going to have a lot more. So current distortion goes back and causes the voltage distortion, but you definitely can have current harmonics, and it comes from the loads. The difference is, think about normal power flows from the utility down to the loads. Think of harmonics as flowing from the loads back to the utility. And it's a little counterintuitive, but that's really the best way to think of it to make the most sense out of it.
Okay. So what I'm looking at here, the dark line is your voltage, and those humps are on your current?
The current, yeah.
Okay.
That's for variable frequency drives, for example.
All right, perfect. Okay. So the true or false is the right answer on this. If you pick true or false, you were probably in the right ballpark.
You win.
You win. The not sures, 28, and the 15 that says no such thing. Hopefully we learned something today. In typical industrial applications, voltage distortion causes current distortion. 100 people said true, 37 false. What say the panel of experts? Eric, wake up, buddy.
He lost connection.
Oh, he lost the connection. We can see him. We just can't hear him.
He's buzzing. All right. So, yeah, no, it's what we just said. Yeah, it's current distortion causes voltage distortion, and in most cases, right? I mean, there's some weird applications where a generator will create voltage distortion, but for the most part, it's current distortion causing voltage distortion.
So, Dan, like you taught me, in the case of a drive, the drive pulls the harmonic current in, which then you got harmonic current drop back to the bus, which then causes the voltage distortion. Yep.
Yeah, if you go to the one slide that says harmonics, it's not that complicated. It has like heating problems. It's a yellow slide in the middle. It's harmonics. It's not that complicated. It's called. Harmonics. That's probably the easiest one to explain all this.
All right, so hold on. Let me.
Eric, I think Eric's back.
No, he's completely out. But hold on. Let me just do 3. So there, I got the slide up. If you want to talk about it.
No, the one that it actually is called harmonics. It's not that complicated. It's right towards the beginning of the harmonics section.
Harmonics
should be up a little
not
ways.
that complicated.
Yeah, keep going up. Keep going up. Right. Oh, actually, it's purple. Right in the right side, second row, right side. Yeah, there you go. Okay, so let's run through that. So we try to overcomplicate harmonics. So if you say, go to the next thing and you say, well, harmonics is really just Ohm's law. So voltage equals current times impedance. So like Santino was just talking about, what happens is, go to the next click. So basically, if we say voltage distortion is related to current distortion times the harmonic impedance, basically what happens is, let's say you have a warehouse and you add a whole bunch of, you say, okay, I've got all these conveyors and stuff, but I'm going to add variable frequency drives. So now my current distortion goes from 0, which is all 60 hertz motors. Now I'm going to put current distortion out because of these drives. And so the next step is go to the next click. As soon as you do that, you're adding, increased harmonic currents, and then you're going to cause heating problems. As you do that, the current distortion, if you go to the next click, is directly proportional to the voltage. So then the more current distortion, the more drives you add, the more you screw up your voltage. The more you screw up your voltage, the more potential issues you have for other stuff. Okay. Now, the next step is, if you click through one more, now what happens is, you're adding more. So yeah, you get more voltage distortion. The next click would be if you put on a generator. So now I say, okay, my harmonic impedance right now is 5.75. Switch to my generator, it's 18%. So I've increased my impedance by 3 times. My current is the same because I have the same load. And then if you click one more time, then the voltage distortion goes through the roof. And that's what we saw, with the situation there. So again, current distortion generally causes voltage distortion because it's directly proportional. And then depending on how much impedance you have, you could have a significant amount of voltage distortion or a little bit of harmonic distortion.
Interesting. All right. Okay, so bear with me here because we're missing a few people, but we lost Eric, and that screwed up my screen. So I just got to figure out how to fix this. 1 second, okay? All right. So we got Santino back. We're missing Dan.
Back in action.
Let's do this.
A little bit of tech difficulties. Eric's phone dropped off.
Yep,
WebEx.
I figured that would happen. You never use your phone ever. Big no.
The mobile one.
Mobile one.
Yeah, that's mobile one. We lost mobile one. We still have my computer. I just don't have my phone.
Ah, gotcha.
The immobile one.
All right. Well, here's what I'm going to do is I am going to go back to PPT wide. I got to get Dan back. So 1 second with me. Whoop, 1 second for me here. Oh, I got to do this. So what we're going to do is I'm going to grab. We're going to go in and look at the Mentimeter again. So I'm pulling you back up, Dan. I got to get you back in here. So it's just the 3 of us. So just bear with me. This is what you get when you're live. This is what I love about it. Because you got to be on your A game. And watch this. Bam!
There it is.
We are back in the saddle. All right, so let's do typical industrial applications, distorting clauses. All right, so let's do the next one. Measuring motor current on a motor that is not connected to a drive or soft starter. It will never have distorted current. Looks like everybody says false. I think that's about right?
Yeah, what happens is basically you get voltage distortion from other loads, and then it'll have current that's reflective of the voltage. So if you have voltage distortion, what you end up with is current distortion on the actual motor that's crossed the line.
Ah, okay. So so the right answer to that is being displayed. Would we agree?
Yes.
Okay, so that's 123 people that are absolutely correct.
Are you getting a split screen?
Yeah, the one on the right is live. The one on the left is not. All right, so let's do this. Let me grab this guy. was going to try to fix you before, but I'm going to transition over. I'm going to fix you while we're live. All right, Dan. Why don't you talk us through this one, buddy? This is output current harmonics. So this is controversial, right? So output current harmonics on a VFD. Oh, this is a good one. This is a good one. So hold on here. Let me just, I got to fix you. I got to fix you up 1 second here, buddy. Hold on. There we go. Let's try this one for a sec. I'm going to move this one for a second. All right, go ahead. Why don't you hit this one up while I fix this other one? So have at the output.
So there's a question usually that are the harmonics that you care about the ones that are going into the drive or out of the drive? And the real answer is that it's the ones that are going into the drive, because what happens is if we think about it from the load perspective, what's coming from the drive going back into the power system is coming in from the rectifier part of the drive. So think about a drive as basically a rectifier going AC to DC. And in the middle, you have a DC bus, completely electrically isolated from the source side. And then on the output, we have what's called pulse width modulation in 90-some% of the drives that you have out there. So, a high percentage anyway. But you basically have the inverter part of it that's going to have high frequency voltage, but the current actually going into the motor is fairly linear, but obviously a different frequency, because that's the reason we buy a drive, to change the frequency. So what you end up with is the current harmonics on the input are the part that you care about, because that's what's going back into the power system. The harmonics that are on the output are really more voltage related, but typically not related to system problems, or related to motor problems, cable problems, issues with the motor itself and the loads, on the output, and maybe interference from that high frequency pulse width modulation. The interesting thing is you get a really crazy voltage waveform that comes out of a drive, but in fact putting it into an inductor, which again 2 pi times the frequency times the inductance, you're going to end up with that inductance slows down any current coming out of the PWM voltage source. And so you end up with a fairly sinusoidal waveform. It could be 30 hertz or 45 hertz. Anyway, answer should be anything coming from the source. So in this case, the output harmonics are not really the ones we're concerned with.
Okay, so that's not going to hurt my motor then. So I can have a variable frequency drive. I can put a lot of harmonics on there. That's not going to hurt the motor?
Well, again, the harmonics that we're concerned with, the ones we showed on that picture that you showed previously, those are the harmonics. That's the waveform that's going to the drive, meaning that's the harmonics that are coming and pushing back into the power system. The ones that are going to the motor are the pulse width modulation voltage, waveform, so it's a voltage source. And then because it's an inductor, you end up with a fairly linear type current. So it's not the current that hurts the motor so much as the high frequency voltage issues that could present problems. And it's usually more of a transient type issue.
Now, what about negative sequence? I know negative sequence currents come into play here. When is that raised from an awareness perspective because negative sequence currents act to restrict the rotation, right? And they add losses.
Yeah. There's a slide called harmonics and motor heating, and then harmonic or motor heating and vibrations. So if you can go to those two on your PowerPoint.
Okay, that's what I'm doing right now.
So there's the one that we just talked about a little bit ago. You have a motor that's across the line, but it's actually drawing current because of the harmonics coming out of the drive. It's screwing up the bus voltage, the 480 volt bus. Then that motor on the left draws a non-60 hertz current. That was the question we just had. Now, if you go to the next slide, which is basically the motor spinning one direction, and the negative sequence harmonic currents want to spin it the opposite direction. And in fact, that's it's like driving with your foot on the gas and the brake at the same time. You're going forward, but you're kind of resisting the forward flow. And negative sequence ones are going to be like, it goes positive, negative, zero, positive, negative, zero. So it's like first, second, third, or fourth, fifth, sixth, seventh, eighth, ninth. So if you think of negative sequence, it's positive, negative. Negative would be second harmonic. Then positive, negative would be fifth harmonic again. So second, fifth, Those ones are the ones that try to spin it backwards.
All right, so I got to put a shout out to Mike Holt because he lets us use this image on our slide, so that's a good thing.
Yeah, I did a session with him a long time ago, and he gave me that to use in
Awesome.
presentation. So
Awesome.
yeah, no, it's a good slide.
Yep. And okay, so we already looked at this one. So we're good with that?
Yeah.
Perfect. Yep. Oh. All right, there we go. We ready now? So the right answer for this one is false, right?
The output harmonics, yeah.
Yeah. So it's we really are concerned about those input harmonics on the input side because it impacts the rest of the power system.
Right.
And then someone wants the check please again. That's okay. We still love you. That's what we're here for. All right. I think we're almost done. Active harmonic filters, although expensive, solve all harmonic issues. One-stop shop. True? False?
Go ahead, Eric.
Can't hear you, Eric. I'll unmute you. Hold on. There you go. Speaking.
Thank you. Yeah, it wouldn't let me unmute it. Yeah, I'd go with false on this one. Active harmonic, they're great, but I mean you can't solve everything with them.
Yeah. So what does an active harmonic filter do?
So it's going to actively monitor the loads. So as you change your loads, it's going to actively input equal and opposites. Like as far as we can actually show it here. So we'll.
Yeah. Why don't we? You want to show it?
Yeah.
It works just like noise canceling headphones, right, guys?
Yeah, that'd be cool. Yeah, that's all right. I think we could show it, make a lot more sense out of it.
Let's do a demo. Come on.
Here we go, Mobile Cam 1.
Oh wait, yeah. So what video? So I don't see anything on Mobile Cam 1, Eric.
Mobile 1's coming back.
Mobile 1 Kenobi is coming back.
So essentially, the active harmonic filter is sensing constantly what's going on the bus and injecting an equal and opposite current in order to cancel that out to essentially get as linear of a load shape or load profile as possible. So it works on the same principle as noise cancellation does, where if you have the headphones on, whatever noises are going on around you, you have sensors, and then there's a control system in there that implements and replicates the exact opposite sound, and it shoots it in your ear. So when you actually have noise canceling headphones, you're still getting the sound, but you're getting the negative sound, so you get wave cancellation, so then your eardrums don't vibrate because they cancel each other out, the both noises.
That's so Santino, we got 2 empty slots in between us. You tell me when you're ready, when Mobile 1 is ready.
Can you hear us on there?
I can hear you.
Mobile 1 there? Yeah.
Yeah.
Can you see us on Mobile 1 there?
I can see you on Mobile 1. What I'm going to do is I'm going to put you, I think I have a Mobile 1.
You want to start with the motors? We'll just show that.
Got a good question for Ryan for later too.
All right, so let me there's Mobile 1. That's your MG sets. What is that? What are you looking at there, Dan?
So yeah, so what's going on there is we have a motor on one side connected to a 60 hertz source. Let's say the back side here, okay? And then the one on the front is connected to a variable frequency drive. And think of it like a windmill. It's basically like an induction generator. So we spin this one faster than 60 hertz, and we actually push that one. So it's like drawing current over here and pushing over here. So the only difference is like windmill, like a lot of induction machines, you need to supply the bars this way, but we can actually produce watts going out that way. So we're actually overspinning this one to like 61, 62 hertz and pushing power. The reason we do that is because this one we're going to connect up to some drives. So we just want to show you that we're actually loading these drives. And we'll come over here, we'll start up the motors. You hear them start. We'll shut the door there. Now if you come over here, we're going to turn on our, we have a bunch of variable frequency drives here. So in each one of these has a little different setup. We can do start stop on each one of them. But basically, one of them has extra features with reactors on it. One of them has extra features with different filters. One of them has, but we all have phase shifting on all of them in the reactors. Some have active front end or ride through. Now, If I go back here, I'm going to start up all the drives. And what we're going to do, you're going to hear that running. We're going to take a look at, can we go on your, so Eric's going to switch you over on his normal feed to what the waveform looks like, okay? So can you see that on your end, Tom?
Yeah, we got it covered.
Okay. Now, what we're going to do is let's look at what an active filter actually does. So come over here. Here's the active filter. We're going to actually turn this guy on. And when we do, it's going to inject equal and opposite harmonic frequencies. And if you look at the waveform on that screen now, that's what it actually injects. That's what he was trying to say in words. That makes sense.
So
So this unit is injecting equal and opposite frequencies to cancel out what was there to begin with. So let's go back to the harmonic spectrum on the original waveform here. So we'll turn this off, okay? We'll go to harmonics and we'll take a look at the harmonic frequencies. Now these are all 6-pulse drives. So there's a rule of thumb that says that 6-pulse drives draw current that is 6 plus or minus 1 in terms of the frequencies. So 6 plus 1, 7th harmonic, 6 minus 1, 5th harmonic. Now you can see there that the 5th harmonic is a certain value. In fact, we'll go over to that. And what's that work out to be? Is it like 40? It should be about 40 amps or so. So what's going on is we're going to turn on the filter now. And what it does is just like a noise cancellation headset, it cancels out or negates all those currents by putting current that's 180 degrees equal and opposite of that. So let me just kind of pictorially show you what that means. Let's just put, you got the mobile camera here once, Eric? So just show me like here. So let's say here's a drive, right? So this drive is pushing current back out through the system. It goes up to the bus, okay? There's 4 bus plugs up there. Those 4 bus plugs are these 4 drives over here. So if all those currents, if each one was putting out 10 amps of harmonic current, 40 amps of current would flow down that bus. It goes back up through the main switchboard, and it goes over here. Now, where does it hit most of its impedance? It goes to the switchboard. The busway doesn't have much impedance. The cable doesn't have much impedance. It goes through here, and it hits this guy. This is where most of the impedance is. So when we go to the
what is that guy?
We're going to have a lot. That is the transformer, right? So we have about 5% impedance or so on this transformer, and that's where most of the voltage drop occurs. So that when you see the waveform that you're seeing, notice how the voltage is distorted a little bit, right? In terms of, let me go back to the waveform here. So see how the voltage is a little bit screwed up? Okay. Now, what I'm going to do is I'm going to switch over the source, and I'm on the sag source, so I'm gonna lose it for a second, but we'll start it back up. Anyway, I'm gonna turn this off, and we'll turn these back on. Okay.
Yeah, we got a question.
Go ahead.
How come the 3rd, 9th, 15th harmonics unfiltered are so small?
So on 6-pulse drives, the standard harmonics you're going to see are going to be 6 plus or minus 1. So the 3rd, 5th, all the triplet harmonics are going to be basically negligible. The only reason there's any here at all is because we have some computers and stuff in the building, and that's contributing to our single-phase harmonics, we would call them 3rd, 5th. And we'll show you a slide on that particular one in a couple of minutes here, but that's why they're so small. So if you look at that voltage now, what you'll see is some distortion. If I switch over to an alternate source, what would that alternate source be, like a generator? Now look how screwed up that voltage is, Tom. You see how that is when we mimic
Yep.
like running on a generator. So even though the current's basically the same, we have the same current roughly. Because we're on an alternate source, we don't have good clean voltage. So
It looks
now
like we got a big problem there, Dan, with those zero crossings.
exactly, and that's where the problems come in, right? And so here's the thing. That's not the utility's problem there, right? We've screwed ourselves up there. Now, what do most people do? It's really interesting. What do people do? They go, well, we have a problem when we're on the generator. So let's turn this off. We'll bring in a load bank. We'll turn on some linear load. And so now you see nice clean current. Then we'll run our generator test. Oh, look, it's fine. It's not the generator, right? But in fact, it's the interaction of the harmonic currents, again, produced by the loads, interacting with the generator. So if I leave that same load on, turn my drives on, now I see that distortion again.
Wow.
And if I turn, and so the answer is turn all your drives off and your harmonics go away, right? That's easy. So anyway, we buy drives for a reason, right? We buy them to make our life better from an efficiency standpoint or control standpoint. And that's really the key is all these things are interrelated and trying to figure out like how this stuff works. In this case, this stuff is something we're screwing ourselves up with. We're causing that problem back on the system.
Well, that's pretty cool.
So like Dan was saying earlier, when he had it on the utility source, the drive is causing that harmonic current and that's to go somewhere. But when you have the transformer, such a low impedance, it's able to sneak through that and not cause as much voltage distortion. But when you have the generator, that's such a higher impedance that less gets through. So you have a larger voltage drop, which results in more voltage distortion. And that's a weak source, the generator.
Absolutely.
Another good question for you, Dan, from Ryan Jackson. Are some harmonic orders worse than others or just different concerns? And I would say it's not necessarily the order that's causing the problem. It's just that the lower order harmonics are of larger content and such, and thus those are the ones that do the damage. What would you say?
That's right. If you think about it, you're exactly right, Tino. So most of the time, the characteristic harmonics, we'll say, are going to be, like lower order harmonics. So you see more like third, fifth, seventh, depending on what kind of system you're on. And Tom, there's a slide that I'll try to find for you here that'll show that. But basically, the characteristic harmonics are going to be, again, fifth, seventh for drives, but the 11th and 13th are smaller, as Santino's saying. So they don't really contribute as much of an issue in terms of like how much they cause problems on the system. But so if you looked at the 19th harmonic, there might be some there, but it's going to be so small, generally speaking, it's not as big of a deal in terms of the magnitudes. And it really comes down to the current amplitude, not necessarily the percentage, which can, again, become misleading if you're not careful. So, yeah, that's the case, exactly.
But something else real point out, Dan, was the fact how they, like you said in there, like the most expensive, it could do everything. But what else can you do before you get to that active filter kind of level? Is there something else you can put in that'll kind of maybe minimize the size of it, so maybe it's not as expensive? Like, is there something to think about there?
Yeah. So Tom, there's a slide called "How Does a Filter Work?" and I'm not sure which one that is in your slide deck.
I'm going to search
I don't know
for
if
it.
you can find that one. But basically, there's always good, better, best, right? So if you think about the least expensive thing for minimizing harmonics is line reactors on drives or impedance in front of equipment, because again it minimizes higher frequencies, and that's what we're talking about when we're thinking about harmonics. They're higher than 60 hertz. So if you click through this one, Tom, just kind of click through until you get the arrows up, and it'll keep going until you see 24 amps going towards the filter. Yeah. So right now what you're seeing is if you have all these drives creating this harmonic current, and really be truthful, I should have put the arrows on top of the drives, not on the motor side of the drives. But anyway, each one of those drives produces a certain amount of harmonic current. Let's say 36 amps total, 12 from each one. And we're talking about each of these frequencies. So the fifth might be 36 amps. The seventh might be, 15 amps and so forth. But again, like Santino said, by the time you get to the higher order ones, maybe you're at 1 or 2 amps, it doesn't matter. Anyway, if you knew that you were trying to get rid of that fifth harmonic, what could you do? If you had a filter is an inductor and a capacitor in series. Essentially what you do is you make that path very, very low frequency or very, very low impedance for a particular frequency. So, well, ultimately what it becomes is we tune it. We create an inductor that has like at 300 hertz, or actually it's a little bit less than the fifth harmonic, we would tune it. A lot of times you'll hear 4.7, 4.8 harmonic, something like that. But anyway, you would make that filter at that frequency of interest become almost like a short circuit. So what's current going to do? Current's going to always go to the path of least impedance. So as the current goes up and it finds its way up, it says, okay, the utility looks like a good path. The generator isn't really a great path, but the filter looks like a reasonable path. So as Eric mentioned, this is, this would be step 2. So reactors would be 1, filters would be 2, active filters would be, another step in the process. So you have to look at, the best cost, method for harmonic reduction, accordingly. But certainly from a system standpoint, active harmonic filters are much easier to apply because you don't have to do a lot of calculations and other resonance things and things like that. Whereas a lot of times with filters and other types of devices that have a current rating that can be exceeded, then you could run into trouble if you don't size it right.
It's something cool to point out real quick while you're on that slide looking at that. Like you just said, it looks like a lower impedance, so it's going to want to go into the filter. But where does it go when it goes into that filter? A lot of times people think that it goes in there and maybe it goes to ground. Like as far as like where is that going to go? So it's not really obvious that it's going to go into the filter and it's going to go right back to the load on the other 2 phases. So if it came in on A, it's going to go back on B and C. So
yeah,
something
that's a
to
really
think
good
about, point out.
Eric and I talk about that a lot here because like a lot of people think, just like a surge protector, you connect to ground. You want to get that high frequency away from the surge protector, or away from the system, take it to ground. But in a harmonic filter, it goes in on A, back on B and C, or if it's single phase, it could be in on A and back on the neutral. But that's something that, a lot of people don't really recognize or think about. So you're really not taking the harmonics off of the system. Current has to flow in a loop, right? So it goes out of the load, back to the load, out of the load, back to the load. And in that sense, it's really just going out on the phases and back on the other phases. Where it stops is at the filter point. And if you notice, all of it doesn't go into the filter, only in this case about, half or so. And that's the other part is, what if all of it went in and then you added more drives? All of a sudden you might overload your filter and damage it. So you have to, that's why it's difficult to size filters without knowing what the future would bring.
So we got a question from David Engelhart asking, he says his apprenticeship days told him that capacitors were used to correct power quality issues. Is that still applicable?
So there was a time where people would use power quality and power factor as the same kind of term, but power factor for sure. You could use capacitors to correct power factor problems. In fact, if you put capacitors on with harmonics, you could have somewhat of a disaster in some cases, right? So you could have interaction, and there's a slide, the harmonic resonance ones, Tom, that we were looking at, which would be, I think it's just titled harmonic resonance.
I'm looking for it.
Or resonance. It has the Tacoma Narrows Bridge. So if you've ever seen the video of the Tacoma Narrows Bridge, it's a very famous kind of story where, and actually if you watch our one video called Harmonic Resonance, you'll see Grandpa Santino act this out. It's pretty cool. But basically what happens is the bridge, if you remember, started to oscillate. And do you remember why the bridge oscillated? It was the wind, right? So the wind was moving it. So if the wind didn't blow, the bridge would have just sat there. They had a mechanical resonance like a guitar string. It doesn't move until you pluck it, right? So in this case, if you go to the next slide, what happens is capacitors on a power system have an electrical resonant point, but what happens is they don't resonate, they don't oscillate until we inject something into the system. In this case, it could be, whatever frequency we're putting out of the drives, fifth harmonic, seventh harmonic, whatever. And you see the top picture is a capacitor that blew up, medium voltage cap, and the bottom picture is a capacitor that blew fuses. So If you get lucky, you blow the fuses. If not, you could blow the equipment up. So that's a great question. You still apply capacitors for power quality in the sense of power factor, because some people can use that same thing. But in the sense of trying to correct harmonics, it might actually, or it will actually amplify the harmonics on the system. So what you do is you convert that capacitor into a harmonic filter, which still looks like a capacitor, except it has an inductor in front of it. And you actually use it to control the harmonics.
Something to bring up too that I didn't know about at first was as far as those capacitors in those filters, those aren't just standard capacitors. Those are actually like filter capacitors. It's the same kind of thing. So it's kind of derated, so to say. So it's something cool to think about. Yeah, I'll just grab it and bring it over here.
We have a one-of-a-kind demo that actually can enhance these harmonics.
Which one do you want me to grab?
That we have in the PQ lab where Eric and Dan are. There's a video of it on the website.
That's another good point. What I'll do is I'll put some links to the videos, various videos that we have on down below this.
I was just showing the Tacoma Bridge in our video that we did.
Yeah.
Kind of falling over.
So what's Eric?
So there's a capacitor inside. There's fuses on top. Now, if you look at that capacitor, it might look like a standard one. It may be a standard one, but what Eric was saying, if you make it into a harmonic filter, you put an inductor in front of it. What happens is there's a voltage drop across the inductor, and then there's a voltage rise across the capacitor. So again, we're connecting those typically line to line. So if you have 480 volts and you have a drop and a rise, that means, let's say you drop 20 volts and you rise, and your whole voltage is 480 volts. That means the capacitor has 500 volts on it all day, every day. So you have 20 volts down, 500 volts up. So if you use the standard capacitor, it would be stressed all the time and it would fail. And that's really the key, is you have to use what they call harmonically hardened, which essentially is like an overrated capacitor, usually 550 volts or 600 volts on a 480 volt system. It's kind of like, think about it like a K-rated transformer.
That's what I was going to ask. Is that so we have I guess you'd say power quality and
harmonically hardened.
Yeah, thank you. Harmonically hardened capacitors, but we have the same thing in transformers as well. But you think about a transformer as a big hunk of iron. What do we do different in a harmonic from a K-rated transformer? What's so different about that?
So Eric will show you real quick on the mobile camera there, the two transformers in the corner here. Okay. And if you look at those two, the one on the right is a standard 75 kVA transformer. Is a K13 or K-rated transformer. So what's really different about them? Essentially, the one on the left could be 100 volt transformer with a 75 kVA label on it, because ultimately, if you put too much harmonic current through the transformer, you're going to end up heating it up. If you end up heating it up, what happens is you end up with a premature failure. And there's some thermal pictures in the PowerPoint slides and stuff we showed. But essentially, K-rated transformer is essentially living with harmonics. So think about it like the capacitor example. We're able to withstand it. It's not like we're getting rid of it. We're just saying it's kind of a Band-Aid approach. We're living with it, right?
Right.
Same thing.
Well, that makes sense. So we're taking that transformer, beefing it up to handle the heat. Is it just primarily heat, right?
Yeah. And sometimes we work as a manufacturer. We work on the inside of it too to make sure that we can kind of minimize the harmonic currents to go through it, almost like an inductor would react. And instead of making the impedance smaller, sometimes we make it bigger. It really can help to reduce the harmonic currents through the system.
All right. Okay. Well, that sounds cool. So we got another question here. When it's said that harmonics result in increase in technical losses, this actually means increase due to individual harmonic components only. Really?
Cosine 60 hertz. I think so that is.
Is that
Transformer
right?
losses, or
When you said that harmonics will increase technical losses, this actually
He says, so when it is said that harmonics result in increase in technical losses, not sure what that means. This actually means increase due to individual harmonic components only. Really, I don't know, cosine or cos 60 hertz losses will be there anyways. I'm not sure if I...
Yeah, so there's a slide that's called System Inefficiency with Harmonics. I don't know if you can find that one. There's a graph that with and without harmonics on a transformer.
Inefficiency.
But, so what happens is we've done a bunch of testing, and what you find is, yeah, the 60 hertz losses are going to be there, but then the harmonics are on top of that. Yeah, so if you look at the blue curve, that's the efficiency of the transformer with harmonics, 100% harmonics, meaning fully loaded with computer power supplies. The red graph would be just 60 hertz on the same exact transformer. So a lot of people say, oh, get rid of all your harmonics and you'll save 50% of your bill. Well, it adds another % or two of losses, but it's not really, it's not doubling the amount of power used. But it's a great point that it does contribute to losses on transformers, cables, part of the power system. So, and if you notice too, the one interesting thing about that curve I'll point out is with all the new transformers, there's been standards for the past probably 10 or 12 years now that as manufacturers, you notice how the curve kind of goes up in the middle and kind of goes down?
Yep.
It used to be that transformers were designed to have the highest loss or the most efficiency at the highest load. But what they found was dry type transformers are generally loaded about 35%. So the interesting thing is manufacturers design transformers to be most efficient at 35% load, which if you think about it, that really helps for designing standpoints.
That's interesting.
And especially with harmonics.
Yeah, that's really interesting. And especially since, we're doing a lot of changes in the National Electrical Code around load calculations to utilize this equipment. I guess if you follow the load calculations and the adjustments that we're making, you're going to be basically operating this equipment higher in its percentage of full load. So we'll be outside of that range of efficiencies because we've designed it down there around the 35%.
Yeah, I think it's TP1 standards that they're pushing that or have. Go ahead.
Tom, that's particularly interesting to me coming from the field of power electronics. One of the things we do with power converters is that type of efficiency optimization. So it's kind of like a timescale thing where, Dan was saying at 35%, they operate there most of the time. So if that's where you're most efficient, then, that highest efficiency for that highest period of operation is going to yield your highest overall efficiency. Yep. So those trade-offs, there's a lot of interesting mathematics that go into that.
Yep. So I saw another question in here. What's the recommended maximum distance between a harmonic filter to a variable frequency drive? Is there?
Sorry, can you repeat that? What's the maximum what?
Distance. Is there a distance issue, like electrically, where you place a harmonic filter to a variable frequency drive?
Yeah, so that's a good question. So if you think about the picture that you showed earlier with how does a harmonic filter work, and again, how, Eric showed you the busway and the cabling and everything around here, most of the impedance, if you're doing a fault calculation, you would really consider it in the transformers and everything upstream. So if you're on the same, I'll say, voltage level part of the system, 480 volts or 208, that current's going to want to go to that filter most of the time, as long as you're between the transformer and the load that's creating the harmonics. Where you have problems, if you try to put the filter on the other side, it may or may not go that path, and you're certainly going to have voltage drop on the downstream side of the transformer. So you want to have it on the load side of a transformer for sure, but harmonic currents really don't want to flow to other loads because the impedance of the other loads, if you look at a motor, if you look at any other load, is fairly high. So the nice thing about harmonics is, again, using that simple calculation of Ohm's law and thinking about current wants to flow to the path of least impedance, it's going to want to go to the filter as opposed to going back on the system or going to other loads.
So you were saying, Dan, you when you said on the right side, you're saying don't put the filter on this side of the transformer.
On the source side, right.
On the source side. And with regard to, like, for example, if this was a lineup, if this
It's
filter,
not really that relevant. Yeah, it's not really that relevant because that bus is such a low impedance.
okay,
These currents are going to see that. So proportionally, the transformer is 100 ohms compared to, zero point 0.5 ohms. Or, you know what I mean?
Right.
It's not those numbers, but it's significantly less, no matter where that filter is on the bus.
you're not going to cause any currents and interaction between the drives and that filter based on where you place it on the bus or anything like that.
Yeah, the only thing you might run into again is you might push current where you don't want it to go, which could be a problem. So if the current's natural path would be to go back to the source and you put a path that has less current capacity, maybe you make the cables too small, that could be a problem. But other than that, that would be the only concern,
Okay.
Current's going to go where you give a good short path to, in terms of impedance.
Excellent. All right, so I see Bruce is saying he's seen where K-factor transformers are wound with 4 square, closely packed conductors on each secondary phase. So it looks like they probably will be the K-factor transformer, which may be beefed up a little bit from a heat perspective, like we talked about. There's probably design principles in that transformer that will help maximize that heat dissipation.
Yeah, and then there's that one, and there's harmonic mitigating as well, and they might do zigzag winding. So there's different designs that actually help to actually reduce or eliminate some of the harmonics as well, and that's all done and that's why, frankly, they add up in cost and they get more expensive, right? So that's part of the whole issue of, well, I'm paying 2 or 3 times as much, am I going to get the benefit out of it, right?
Right. All right. Now we do have one other. There's one more question we got to get through before we get into anything else. Percent THD for current is almost always higher than percent THD for voltage. True or false? And then we have 11 people who want to know what is percent THD. So what is? Let's answer that one first. What is THD? Total harmonic distortion?
Yeah, and I'm going to try to find the slide for it, but they.
And that's not Thomas, like, I'm TAD, right? So it's not my initials.
Yeah. Unfortunately, I don't have a good reference for you to give you that one. I can maybe email it to you if that makes sense. But basically, here's the thing with total harmonic distortion for current. Usually, it's in the 20, 30, 40%, could be those numbers. The total harmonic distortion calculation is basically add up all of your harmonic currents and then divide by, and take the square root of the sum of the squares of all those, so an RMS value, and divide by the fundamental. So what you have to think about is at a very light load, your fundamental is your 60 hertz current, could be very low. So your percentage THD could be high. When you divide by the fundamental from a voltage standpoint, it's almost always the same number. It's almost always 480, 485, 475, 208, 210, 206. It's not that far off. So your values, first of all, don't change with load. And then secondly, the amount of distortion, like we said earlier, is caused by the current. So the more current you have in the system, the more you script your voltage. But your voltage distortion, you might get a little bit of voltage distortion. We could do a quick demo and just show that on the actual waveforms. But let's do a quick demo. I'll show you what I mean on there.
Okay.
If you can throw I'll just talk through it and just put it on the camera if you can, Tom. On Eric's
mobile one.
Eric's gonna put not on the mobile one, but on the
Oh, okay.
the projector of the screen. Yeah. Okay. So I'm gonna try to see what you're seeing here real quick, just to make sure. Okay, so that's our voltage right now, and let's just say we put on some current, linear current. Okay. So that current could be like putting on cross the line motors, and essentially our distortion is really negligible. It's really nothing because there's no current, there's no difference in the wave shape from a 60 hertz standpoint from the voltage and current. Now there is a phase shift. If you notice that current lags the voltage, so that's where the power factor part comes in, right? But the current and the voltage look the same as far as the wave shape. Now if I go to my drives and I put on my 6-pulse drives and I basically turn on, you know, one of the VFDs, for example, I could have a much more screwed up current waveform than voltage waveform. And so you see how much more the current doesn't look like 60 hertz than the voltage. The voltage still kind of looks like 60 hertz. And if I have more and more drives on, turn all the drives on, even still, the voltage still looks more like the current. So now the voltage still looks more like 60 hertz. So let's go now to THD. Let's go to the THD and we'll start with the voltage distortion. So the total harmonic distortion for this system right now looks like it's about 6.7%. And what are the harmonics that are associated with this? Third, fifth, seventh, almost all the odds. In fact, most of the third harmonic is coming from something other than what we're putting into the system here. It's probably coming from the front of the building. But let's look at the current distortion. See how the current distortion is like 38%, 37.9%. But the harmonics that we see are the ones that we expect. 5th, 7th, 11th, 13th. Those are the ones coming from the drives. So the current turns into the voltage distortion. Now, if I did something like this, we'll just leave it on that screen right now. Okay. Now it looks like my percentage goes down, right? In fact, let me do one other thing here once. Okay, so we're at about, what, 26.7%? But let's start at 26.7%. Let's look at the fundamental, the 60 hertz. So again, total harmonic distortion is adding all the harmonics, squaring them, divided by the fundamental. The fundamental right now is 160 amps. Let's look at the fifth harmonic. The fifth harmonic right now is about 39 amps, okay? If I change my load right now, it looks like my harmonics are going up. But in fact, just the percentage went up because my fifth harmonic is still about 39 amps. Go to my fundamental, we go from 160 amps to 118. So I'm dividing by a bigger number when I have more 60 hertz load, but it's not affecting me from a harmonic standpoint in terms of current amps. And that's the part that can become kind of confusing. Does that make sense?
It does to me.
Yeah, I want to maybe emphasize from the standpoint of, say, a circuit problem, or what we kind of deal with in circuit theory at school is we're dealing always in the power systems with a voltage source. So, you know, we're always relying on our 120 volt outlet. In this case, we're dealing with an industrial bus that is 480 volts. So we're always dealing with that stiff source, that set voltage, and that doesn't change. And we draw current as we need it. So essentially, if we have a very lightly loaded bus, but say one drive on that bus, the current distortion percentage could be very high because there's not much current going through that bus. Whereas if you had a bunch of other non-harmonic devices loading that bus up, so there was a very high bus current, and you had one drive causing a little bit of harmonic distortion, that total percentage would be much lower because it's canceled out by that large, say, denominator of other currents that aren't harmonic. Does that kind of sum up what you were saying, Dan?
Excellent. Well, that was fun. Can't hear you, Dan.
Yeah, that's exactly right.
There you go.
Sorry, I was getting a spam call. Sorry about that.
Hey, just wanted to reach out about your car's extended warranty.
All right, so
I know.
okay, so there's all right, so there's a couple questions here on YouTube. All right, so we saw that one. So Sanjeev, can you please elaborate if IEEE 519 standards call out for a recommended percent for THD.
Yeah. So, Tom, and this will be in the tables in, again, I'm not sure exactly where it's going to be in that thing. It's kind of towards the end of your PowerPoint deck, I think. And it's going to be, it's going to say IEEE 519, 2014 voltage and current limits.
IEEE 519. Hold on. Wait, is this it? Whoop, I got to show the slide.
Yeah, now, yeah, that's it. So go to the next slide once. So the important thing is, where does this apply? Keep going one more. Yeah, next slide will be like a picture. Yeah. So the important thing is, where does this apply? And a little bit of that's getting cut off there, Tom, but not much. So basically, this applies at what we call the PCC, or the point of common coupling. What that means is where the utility can serve another customer. So usually, if they own the transformer, it's on the secondary of the transformer. If you as a customer own the transformer, it's on the, the primary of the transformer. But essentially, it's where they can serve another customer. And it really goes back to the fact of, they don't want you to screw up your neighbors. They don't care if you screw yourself up with these harmonics, because remember, they're coming from yourself. So good luck with that if you do. But you know what I mean? Like, that's why they don't care. But then if you go to the next, I think, slide or two, there's a table. Okay. Oh, by the way, let's say you had to take measurements. This is an important point. Let's say you had to take measurements, and you're on a 480 volt transformer, and you could take the 480 volt measurements on voltage and current, and you can comply. That's great. But what if you own the transformer and the PCC is on the primary? You might say, well, I should probably measure on the primary of the transformer, but it's not safe, right? So what happens is, because the harmonics are coming from you most of the time, if you can actually measure on the secondary and be compliant, meaning you're below the levels, then that means automatically, because the transformer is offering the most impedance, your current's going to be the same and your voltage is going to be the same or lower. Well, it's going to be considerably lower, as we just saw, on the primary of the transformer. So now if you go to the next slide, it should show the tables, I think. One more, sorry.
That's okay.
One more. Maybe a couple more. All right, there's a table here eventually.
There it is.
There it is. Okay. So it used to be that low voltage systems below 1,000 volts, so again, just calibrating everybody, for 480 volts, 600 volt systems, 208 volt systems, it used to be 5% voltage distortion. They raised that up with the 2014 standard, which was a big change, and they went up to 8%. What they found was equipment can handle more. Going back to the definition of power quality, it's kind of what works for you and your system. And what they found was, people's equipment could handle more. So it's okay to be at 8%. Now, if you look at the next table, there's a graphic for current distortion. And what you notice, and this goes to, like, if you did a short circuit study, you would say if you were on a weak source, you can't have as much harmonics, and if you're on a stiff source, you can have more harmonics. It kind of goes back to a little bit of what Santino was just talking about. Think about it this way. I have a 30 kVA transformer. It just really exaggerated, right? 30 kVA transformer. I have a 30 horsepower drive. What effect is that 30 horsepower drive going to have on that 30 kVA transformer versus that same 30 horsepower drive on a 3 MVA transformer? The impedances are both 5.75%, but they're percentage based on the size of the transformer. So what this table shows is the total demand distortion, which is kind of almost related to the total harmonic distortion, but I'll explain that in a minute, can go up in the maximum amount of current you're allowed if you have a stiff source. If your ratio of your your load to your short circuit capability is fair and reasonable, meaning you don't have a lot of load on your system compared to the size of the system. So, and they define TDD. We talked about total harmonic distortion. Total demand distortion is taking your kind of your worst case scenario, your worst demand of the month, 15-minute window or whatever, and dividing your RMS harmonics divided by that peak demand. So most of the time, it's a little bit more forgiving than an instantaneous value. In fact, if you measured your harmonics overnight, your THD might be through the roof. It might be 30, 40, 50%. You say, oh, it's terrible. But when you're at your peak demand, it might be, 6 or 8, 10%. So that's what this table has.
That makes sense. That makes sense. So you're looking at, instead of an instant, you could have an instantaneous period of time where you have a very poor total harmonic distortion, but it's not going to impact you. It's not something that they weigh as heavily as if it was that way for a long period of time.
Yeah, and I think if you go forward a couple slides, I'm not sure if it's in there or not, but a picture of a hot stove. There's THD versus TDD. Go back to that real quick. Sorry.
Yep.
Go one more.
Cool.
Yep. So THD is basically taking all the harmonics squared divided by the fundamental. TDD is taking all the harmonics squared divided by your maximum load current. And an example of that is actually on the next page, which is actually a good example. If you look at the at a large drive like 225 amp demand load, what you see there is the THD at 30 hertz at half speed is like 26% or something like that, and then the TDD at that same load is 3.6%, but your actual amps of harmonic current are 8.2 amps. So if you're looking under the 30 hertz column, your amps are 8.2. Now, as you load that drive up, you get 9.2, 10.1, 10.8 amps. So your harmonic amps are not increasing that significantly, but what's increasing a lot is your 60 hertz current because you're doing more work. You're adding more load to this. So what's important is the TDD doesn't increase significantly across that range, but it does follow the amount of harmonic current that you add, where the THD goes down, and it can be misleading because, again, you're dividing by a smaller number. You're dividing by that instantaneous 60 hertz part, which always throws people off, and they say, well, I got this 18 pulse drive, and I'm only getting, 8 or 10% current distortion. It's supposed to be less than 5. Well, that's because you're running at a slower speed than full speed. And why do you buy a drive? You don't buy a drive to run it at 60 hertz. So if the harmonic amps are less, that's really what you care about, not the percentage. Now, if you go to the next slide, it goes to that touching a hot stove. And what I meant to say there is, just like you mentioned earlier, it's kind of that instantaneous effect versus, pull your hand away, oh, yeah, that's hot, versus hold your hand on the flame, And that's why they put statistics into the new 519 where they didn't have so much of that before.
You always run into issues with when you use percentages. When, like, for as an example, in these cases here, if my current is very low, my percentages could be very high, but that might not be bad, right? So if I saw you shake your head, yeah. So
you're right.
I mean that could be an issue where if you could have a very high percentage, but it's a very high percentage of a very low amount of current or a very low voltage or something like that. So
I'll give you a good example of that. So somebody mentioned earlier about the third harmonic, and the concern is on single phase loads. There's a big concern for third harmonic current, and it adds up on the neutral. So let's say all your loads were balanced, and you had 10 amps on phase A, 10 amps on phase B, 10 amps on phase C. You would say the neutral current would be 0. But if you had 2 amps different on one of the phases, you say, okay, that 2 amps flows back on the neutral. With third harmonic, you could have 10 amps third harmonic on phase A, 10 on B, 10 on C. Your neutral current would be 30 amps of current. And then 30 amps of harmonics divided by 2 amps of fundamental, your percentage is thousands of percent, right? So it's a ridiculous number. And even though it's a ridiculous number, the amount of amps is not necessarily bad. In that case, it could be bad because it's 30 amps, but there are times where your neutral will be a really, really outrageous. I've seen people with 4,000 amp services, and they're concerned because they have 120 amps on the neutral, but it's 800% distortion.
Right.
Exactly to your point. So you have to have a sort of a good sense of what the actual percentages mean. Exactly right.
Cool beans. All right, so let's take a look at.
So just to be clear on that one, Dan, like
Yep.
as far as the compliance, what do they care about, the TDD or the THD?
And for IEEE 19 is TDD.
Yeah. TDD.
Yeah.
All right, just making that clear. All right.
For sure.
All right, so let's take a look at YouTube again. What power quality parameters are improved when we have a stiffer power supply, i.e. one having high short circuit MVA? That's from Shahriar Khan, Mr. Khan. What do you think?
So one of the things that comes to mind with that is voltage sags. If you have a fault on the power system, okay, think about a utility power system. That's a, pretty widespread, you don't have a lot of control over how stiff that system is, but obviously they do. So the further out you are on that system, the more likely, if there's a fault right outside your door, the voltage is going to be 0. But if there's a fault, 20 miles away, the voltage at your place might be depressed because it's a weak source. If you have a stiffer source, higher voltage system, or much just in general stiffer source, your retained voltage that you're going to see is higher. So you're not going to see as much of an effect. When you see your lights flicker in your house, if you're on a feeder that's on a stiff source, it's not going to be as big of a drop. Whereas if you're on a rural feeder, all of the things that we talk about, whether harmonics or sags, or even sometimes switching transients and stuff like that, get exacerbated by the fact that you're on a weak source. So, there's interesting scenarios where there's ski lodges at the top of the hill, really expensive houses, and then people put in a chairlift, a ski lift, and they put a variable frequency drive on. They complain because of the issues related to the chairlift, but in fact, it's because they want to live out in the middle of nowhere, and that's part of the fact of living on a weak source. So that's a great question.
Cool beans. All right, so let's take a look at some more.
Got one from Sanjeev, kind of in response to the THD current measurement. He said he had a customer, huge steel fabricator, who was showing 273% THD, but they were very lightly loaded. So he just said that this makes sense now. So thanks for the comment there. And another question for Dan. Why are we measuring THD 277 phase to neutral and not 480 phase to phase?
You're on mute, Dan.
I like to talk to myself sometimes. Sorry about that.
When you start arguing back, that's when we worry.
Eric said I sounded fine. So anyway, yeah. So that's a great point. The reason we do it here was because we want to line up the voltage and current together. The reality of it is, you're absolutely right. For a 480 volt system, we should be monitoring line to line, because you want to see what the loads see. The loads see line to line. They don't care about line to neutral. In fact, truth be told, we're on a high resistance grounded system here, so we can really screw up the line to neutral or line to ground voltage and not really have any issues with our line to line. But we do, you do want to see what the load sees. That goes back to the fundamental kind of parts of power quality. Everything that you kind of measure and analyze and everything should be related to what the load sees. So that's a great point. And it's a good pickup. It's just that when we show voltage and current together, if there's a 30-degree phase shift in the voltage and current, it looks a little bit skewed, and it's harder to explain that to most people because they don't understand the phase shift, actually, to explain why we're doing line to neutral versus line to line.
Excellent.
And let me just make a point of going back to the earlier discussion of everything we did. We use kind of the doctor analogy of analyzing power quality. And that's basically to say, if you go to the doctor and you say, hey, doc, I got a problem, he doesn't just automatically go, let's put a cast on your leg. And if that doesn't work, we'll give you a shot. And if that doesn't work, we can do brain surgery or something like that, right? He's going to ask you, like, what are your symptoms? What are you seeing? What kind of things? So we always kind of approach power quality problems from a symptom issue to determine what symptom is, figure out what it is. And if it's something blowing up, it's probably a transient. If it's, if it's overheating, it could be harmonics. If it's, equipment dropping out, it could be sags or voltage variations. And then we kind of look at the source of the problem, and then we apply the solution that's most appropriate. And sometimes that means doing nothing because it costs you more for the solution than it does for not doing anything. So just want to make sure we covered that.
Yeah, that makes sense. You got it. You nailed that one. So how about, okay, so let's talk about this. We talked about recognizing issues. So we even showed some waveforms. We talked about heating issues. So recognizing problems in our power distribution system. Let's see, we got about another 5 minutes before we close off here. What are the
Tom,
key
your
takeaways?
mic's a little quiet now.
I'm sorry?
Your mic's coming.
Oh,
your mic's
I'm
coming
sorry.
through a little quiet.
Yeah, I when I move away from my mic, I'm
Okay.
I'm all screwed up. But so let's just chat a little bit about. We got about about 5 minutes or so left. What's the takeaway? So we talk about how to recognize issues. Talked about some of the standards and some of the the like where harmonics come from, how to recognize the harmonic issues, right? So we talked about heat issues. What other things? Well, once you recognize it, what's your recourse? How do you? What's the journey on trying to fix issues? Is it a study? Is it throw a capacitor, do some filters?
Yeah, it really goes back to that, analyzing the symptoms and stuff like that. Let me give you a quick example. One of my favorite power quality things. We'll test Santino here and see what he can figure out, right? So, let's say you get a call from somebody and they all have these little baby UPSs under their desk, and they have it figured out in their mind. They got all this cubicle furniture. There's 100 cubes in this office, and they say, on Mondays and Wednesdays, these little UPSs over here beep. And on Tuesdays and Thursdays, those ones beep. And on Fridays, those ones over there beep. And it always happens at 9:05 every morning. So without even setting up a meter, like, how do you approach something like that? What do you think? What would you?
Well, my first question would be is, do you have people working where they're beeping? Is that where the people are working and using them? It's more like a logistical thing, because there's a lot of the real world comes into play. Where are the loads being used? Who's using them? And how much current are we drawing when? So that would be my first question. Can I see, who's on at what time? See if I can get some kind of behavioral assessment based on the power issue.
Yeah, and in an office building, you'd say, and that's kind of the questions I would ask, Eric. Are there any things that come to mind for you?
So I guess I would be thinking of, is there some kind of utility issue that's going on at the same time? Maybe that time of day, if it's happening, are they switching something that's causing some kind of voltage fluctuation that's going to cause those UPSs to kick in? Something along that line.
And then I guess the other thing that comes to mind is, is there a microwave that comes on every morning heating up their coffee or things like that, right? So those are the kind of questions I'm asking. But then when I go in and I say, well, wait a minute, how come Monday, Wednesday, Tuesday, Thursday, Friday? Sometimes you have to take with a grain of salt, and this is probably the most important thing, Tom, I kind of want to point out, like the assessment of the local people that are dealing with the problem, because their assessment is not as people that have been trained to kind of look at this, or maybe they don't have an electrical background, but their memory is going to be clouded by what they remember based on just things that kind of become patterns. And in this case, it's exactly right. So we went down, took a measurement, and it was pretty evident. And so I set up a meter at like right before 9 o'clock and took a measurement. It was, sure enough, it was a utility capacitor switching event that was high enough to actually create these issues with the UPSs. Not really causing anything that caused a problem, except the UPS is alarming and going off every day and going on the battery was causing them to die prematurely. But the point is, kind of going into problem solving, you have to use all your tools, including the people that are available on site to help you analyze what's going on. And then you have to take that information and kind of disseminate it to say, well, wait a minute, that kind of makes sense, that doesn't make sense. And if it kind of makes sense, then you kind of follow that path a little bit. But metering is always going to give you more information. And so the more metering you can do, going back to what you said earlier, Tom, if you don't meter it, you can't measure it, you can't manage it, right? So
Right.
That's kind of my thoughts on where you go with these kind of things.
Okay, so say in your example with this, you were having a utility capacitor switching that was causing an issue. Have you ever run into cases where there was maybe litigation between, if I was the customer and I had a problem, do I try to go after the utility to say, hey, look, I had an issue? I mean, is that, I can see that being a contentious point.
Yeah, no, there's been several cases that I've been involved with where utility type problems have caused problems within facilities. And generally, for the most part, the utilities are doing the best they can, because what they're doing is they're trying to clear faults and things like that. And the reason they're putting capacitors on in the morning is because they're trying to support the voltage for their customers, right? Mm-hmm. The fact that it's amplifying stuff inside the building, again, goes back to the fact that we're putting more sensitive stuff in our buildings. So yes, I've been involved in them. Most of the time, it's a hard argument to make as a customer. So again, gaining knowledge on this topic and really trying to figure out how we can take care of ourselves on our side of the meter is probably the best approach. But there are certainly things that we can do to work with utilities especially on a large scale where it's kind of a predominantly a regional thing, like, oh, this whole industrial park keeps seeing problems, right? Well, maybe they need to cut the trees, trim trees, stuff like that.
Right.
But yeah, it's difficult.
Yeah. So
something I just wanted to add to that real quick.
Go
I
ahead.
was going to add, like, as far as going into metering, like with that example, like, how do you know? Would you go straight to like the main transformer where the utility feeds it, or do you think would you go to like the panel board to where maybe the load's closer to the load, so like at the breaker level, like how do you even start to know where you want to monitor that?
Yeah, it's a great question. So it goes back to the question we talked about earlier. You want to see what the loads see. So the one person who asked the question, why aren't we looking at line to line? If we were trying to figure out what that load was seeing, we'd go exactly where that load is, or as close as we could, and figure that out. Because a lot of times you'll measure at a different location and go, oh, it looks perfectly fine. The other thing that can happen is you might measure something that looks horrible, and it might be unrelated. So just because you're measuring, that's the other caution I'll give you, is that now these meters can pick up all kinds of crazy stuff, and it doesn't necessarily mean that that's the problem. So you have to really kind of align everything. So
yeah.
Good stuff.
Yep. Excellent. So it is 5 o'clock. I do want to continue the discussion though, but it is 5 o'clock, and I do have the Menti code for those of you who have to run. And I know we lost a couple people. And David Englehart's yelling, "Where's that Menti code?" He's right on cue. 175936 is the exit Menti code. We're going to probably have a little bit more of a discussion because I do have some more questions I want to get to from YouTube from our viewers. But remember, go to menti.com, enter 175936. Yep. So I want to make sure they're at the right number, and enter that number, and that'll be my sign out. And again, you sign in, you sign out, PDH certificate, and I will as we go through some of these online questions, I'm going to just double check to make sure that the Menti code is configured correctly. So why don't we do this, Santino? Why don't you read a couple of these other questions and as I look at that other stuff, okay?
Yep.
Excellent.
Alrighty, so question from Sanjeev. And this is probably for Dan because you've really dealt in this area more than any of us. Have you had any cases where there was a litigation or arbitration between the customer and the utility? And he also said, like where, say, the customer got a waveform capture that showed a large voltage swell, and the customer ended up losing a lot of motors or drives from that.
Yeah, I mean, I've been involved in a lot of, especially with the Electric Power Research Institute, EPRI. They work a lot with utility companies, and EPRI has some funds that they work with utilities to try to help customers fix problems that the utility knows is something on their system, but they really can't afford to spend all their own money on it. And so I've been involved in probably a couple dozen projects like that where they spend multiple millions of dollars to try to fix these problems. And usually what happens is the customer pays for part of it, utility pays for part of it. I've not seen too many where the utility is fully to blame for this stuff because honestly their hands are a little bit tied in the sense that they don't know what we have on our side of the meter. One of the things we do is we bring the utilities into this room a lot of times and we say, hey, look at all these different problems that are on the other side of the meter that are caused either in conjunction with things you guys have caused or maybe unrelated, and it's causing this side of the meter, and they really appreciate that. So there's a lack of understanding from both sides of the meter. But for most of the litigation stuff, if something's failed, one good example would be Eric showed you the surge protector that failed. There's a lot of times where an open neutral conductor will cause a surge protector to fail. And in that case, almost always the utility will eventually come around to say it was something that happened. A lot of times they'll go and fix it and not necessarily tell you about it if they can, if they know there's a problem. But if they do find out you had some damage, they'll typically pay for it.
So you have
You're muted.
Following up from me, Dan, have you ever been involved in any of those cases and had to kind of defend either side or?
Well, in our group, in the power systems group where I worked for a while, I've been involved with a couple of the other expert witnesses that had to do the litigation, and I was just part of that. But I actually was in a couple cases where there was some pretty bad issues with customers that got hurt and stuff like that, and it was there's things where you have to really just it's interesting because you have to really think through sort of the progression of this, and troubleshooting and problem solving is, you lose a lot of sleep at night, right? You think of all the scenarios that could happen, and it's not always intuitive. And power quality is one of those things that's just really, it's not intuitive all the time. So like that's to break it down into the biggest chunks and then kind of go down one path at a time and try to follow a logical pattern. But yeah, so I've supported it, but not directly sat in the courtroom and had to defend.
Okay, thanks.
So Ahmed,
Good question, Sanjeev.
yeah, good question. Ahmed has a question, which I think is interesting as well. He says the trend in the world is renewable energy. Photovoltaic may be the most popular method. Grid tied, connected, has a power quality issue problem with any. Do you have any comments? I mean, we have a photovoltaic system on the Experience Center, right?
Yep.
Yeah.
What have you had any? I mean, I know you're capturing waveforms and all this other good stuff. Have you had any power quality things you can think of that would be interesting to talk about?
Yeah, I think part of the problems that we see, certainly on a solar inverter, it's considered a weaker source. So think about what that means on a generator, and exacerbate that by 20 times, right? So all the motor starting issues, all the kinds of things. If you were running a microgrid with a small inverter source, there's lots of stuff you could screw yourself up with a weaker source, which we commented on earlier, but I think it's all related. The other thing is that power electronics can put out, higher frequency stuff, harmonics and otherwise transients and things like that. I've personally seen, kilohertz type stuff, and I've personally seen inverters that have failed prematurely on the field, and I've also seen voltage flicker issues. So you see that with wind applications. We have a video on wind, and one of the things we talk about is the non-consistent sort of pattern of renewables. And so when the renewable source is on and off, there's an issue with voltage flicker. And back in the days where we had incandescent lights, it was just an annoyance because lights would flicker and you'd have problems with that. But now you could actually have equipment that's literally affected by that, and those become, again, very problematic. So
coming from
some of the things.
Sorry. I was going to say, coming from the world of power electronics, I know power factor correction units on the output of inverters is very kind of a hot topic. Maybe not necessarily right now, but I always see those paper titles pop up, like power factor correction for inverters, baked into the actual inverter model, as well as other issues are things like current injection during voltage sag. So, output of an inverter, you got your LC filter. And so if you have a voltage sag, there's a very charged LC filter that can inject currents. So I have a paper with another professor I worked with on IEEE about transient testing, those things that we did at the University of Pittsburgh. If anybody would be interested in that kind of thing.
Cool. Excellent. Yeah. Well, any references you have, we'll stick that up and we'll put that down on the bottom of our YouTube site as a link.
Inverters can affect things like relay coordination, and so not necessarily a power quality, I don't think, issue, but some still an issue with renewables is the current injection and coordination systems for planning and whatnot.
Cool. Trend in the world, we talked about that. Grid tied, menti. Thanks, guys. Before I get to so David Engelhardt, he looks like he's heading out on us. Sanjeev, thank you. Which problem more popular? I'm not sure what he's talking about there. If service entrance panel is full, however, room in panel remains for the surge protected device to mount internal to panel, can it splice into an existing feeder circuit? We just, yep. Okay, so can they splice into an existing feeder circuit? Is there a reason for the manufacturer overcurrent protected device sizing for the SPD? Thoughts on that one?
Yeah, Tom, that might be more of a code question as to whether or not it's allowed to be tapped in, if I understand the question correctly, whether it's allowed to be tapped into an existing circuit. But essentially, one of the things you have to be careful of when you do have a full panel, we see this a lot of times is, people get twin breakers in let's say a residential panel. Yeah, the twin breakers are only on one side of the face, so if it goes A, B, A, B, A, B,
Right.
if you have twin breakers, it's just going to be on A. That's one of the things that we run into. A lot of people put surge protector on it because you have to connect it to 40 volt. A lot of times it'll just be on one side. But yeah, that's more of a code question.
That's
I'm
true.
not 100% sure of. Yeah.
Yeah, you're tapping into. I would steer away from that, because then you've got to think about that conductor. That's a tap conductor inside of a piece of equipment. There are multiple sections and areas in the NEC that I would focus on. Jared, that was from Jared. I think I would have to do a little bit more research to get that one answered accurately, to give you all the code references, but I would say that would not be a good thing, in my opinion.
Dan, the rule of thumb is kind of where this you expect the surge to come from and what you're trying to protect with the surge protector, right? That kind of determines where you want it to be close. So for example, if you had like your television and you had that plugged into a surge protector in the wall, you know your television's protected, but that doesn't necessarily mean that the next outlet over is protected from something that might be the next outlet over where the surge would come from.
Yeah, that's right. And a lot of times that's why you need 2 levels or multiple levels of surge protection. And in an industrial commercial building, it goes usually on each side of a transformer down through the system. But in your home, yeah, it's exactly right. You'd have one even on your main. It wouldn't necessarily protect. As an example, Santino, like you're exactly right. Like let's say your TV was plugged to the outlet and you have a whole house one back at your main panel, but your stereo, which is plugged into the same outlet, blows up. Well, that transient isn't going to go all the way back to your panel, get protected, and come back to your TV. So your TV is likely to get damaged.
Right. The voltage rises right where the surge happens out of the radio, but then to get to the surge protector, you got to go through however long that wire is going to go through the wall, which could be 50 feet. And so there's an impedance associated with that. So.
And we do get a lot of questions on where in the panel it needs to go. But if you think about it, inside the panel, the bus bar is really thick. The wires coming in from the surge protector, 12 or 10 gauge wires. So top or bottom of the panel doesn't matter, because the surges could be coming again from the loads or come from the source. But that's not as important as how close it is in the panel.
Cool beans. Just taking a look and see. I'm cleaning up some of the stuff in. Looks like we picked all the questions up in YouTube. There's a lot of activity. That's a good thing.
We're down to 120 now on the.
They're starting to filter off. We get, here's the thing.
Yep.
As you get past 5 o'clock, you got the diehards now, right? These are the guys who are like.
Yep.
They're waiting. You know what they're really waiting for? They're waiting for something to screw up.
Everybody gets a beer now that's still here.
Yeah, they're waiting for that beer to pop out and then go, look, they drink. Yeah. All right. So you feel like we covered a lot of material. I mean, we could probably go on for days with regard to power quality, and so I think we covered a lot of good material. We did some good demonstrations. We didn't do the surge demo, but we're going to do that next time.
I think, Tom, what might make sense is do one on surge, one on sags.
Yeah.
We could go back and do another one on harmonics, just harmonics. But I think the overall power quality thing, there's so many things to do, but I think if you focus on one, I think it would really, we'd be able to jump in pretty deep. And I'll get you the slides ahead of time this time.
Yeah, no, that's not a problem. And you know what we'll do is, like you say, maybe the next one we'll focus in on surge. We'll pick each of the topics, but we have a platform. This is the first time we've done this together as a team, so I appreciate you guys doing all the prep work up there and getting it all done. And we've got Mobile One on the line, moving around. We got that. We had a couple hiccups, but we got through it, right?
Mobile One's dead. No, Mobile One is done.
Mobile One is done. Okay, throw that thing away, and we're going to come up with a new Mobile One. That's okay.
Mobile 2.
Well, we'll have Mobile 2. That's right. And as these events go on, our future YouTube watchers, when they see Mobile 1562, they'll know. All right.
They'll know.
Okay, guys. Well,
Thanks, Tom. That was fun.
I appreciate you guys taking the time out.
Great. Somebody just asked. Ahmed said, "When's the next one?"
We're going to schedule that one. Thank you, Ahmed. We will schedule it, and if you guys have checked in the registration to be notified, you will get a direct email from us when we do this again. But watch my LinkedIn site, watch Dan's LinkedIn site, Eric's LinkedIn site, and Santino's site. So we will be hitting social media with this stuff, and we'll be posting this. This video will be on my YouTube site, and maybe in the future we'll be able to port these over to some other venues as well, so we can get the information out to everybody. All right. Well, thank you. Thanks to all, to you guys, the team here, and thanks for everybody out there on YouTube sticking around with us and watching and hitting the comments. Remember, hit the thumbs up, hit the subscribe and the bell so that you know when we go live again and when I post some other videos. I will keep all of you up to date on what's going on. So I appreciate it, and I think we are good. And now, Bruce, you get a 10 out of 10, buddy, on the quiz. There's no excuses.
Brought to you by the Technical Social Distancing Network.
Yeah, all part of the Technical Social Distancing. And it is Beer 30, Douglas Strang. Thank you, Mr. Strang. Thanks. Oh, and Mathura Abbasi. There's a guy right there. It's Code Making Panel 2 with me, and I'm looking forward to the public input meetings. It might be digital again this year. I don't know. But, Mathur, thanks for signing in, and that cup is coming to you. I still haven't shipped those cups out yet. I feel very guilty. I wanted to get it out for Shark Week because it was Shock Week, and I still haven't shipped them. So, all right, guys, we're going to sign off. I'm going to end the stream first, so hang in there, you three. I'm going to end the streams, and then so I'm saying goodbye to everybody on YouTube right now. I'm ending the stream on YouTube, so thanks. And stay safe and stay healthy.
Thanks, Tom.
Thanks, Tom.
Thank you, Tom.
Excellent. All right, and I'm going to